Amidst an atmosphere adorned with intellectual pursuits, I, Tejasvi Srivastav from FIPR Student Chapter PDU, have the distinct honor of hosting this workshop on geomechanics with the illustrious Dr. Dharmendra Kumar. His academic journey, crowned with a PhD in civil engineering from the prestigious Colorado School of Mines, USA, intertwines with his remarkable contributions to the field of energy development. As a research scientist at the revered Melbourne School of Petroleum and Geological Engineering, University of Oklahoma, his expertise in computational geomechanics and hydraulic fracture modeling illuminates the realm of hydraulic fracturing. Driven by dedication to renewable subsurface energy systems, Dr. Kumar's vision intertwines with carbon capture, storage, and its utilization, shaping a future where sustainability and innovation converge. Please wait to ask any question until the end of the session because there will be a Q&A session in the final 10 minutes. Now I would like to hand over the stage to Dr. Dharmendra Kumar to continue with the session.
Yeah, thank you for a kind introduction. I'm really thankful to student chapter at PDEU giving me opportunity to share some of my research with the students and faculty there. And I hope that students can get at least some insight in this topic from today's talk. So without further delay, I will directly go to talk. So here is my outline for today talk. First, I will give some introduction about geomechanics and refracturing of horizontal wells, and then give some brief concept and mechanism. What basically controls what is like important for refracturing, and I will give some simulation examples which I have been like doing for like last 4 to 5 years, and so and then I will give some sensitivity analysis. What are the major uh, like factors and component in the refract design and what's impact that the Frac-hit issues. And then I will also show one field simulation what I conducted here at Oklahoma, like in New Vera shale formation here in Oklahoma, and then will be my conclusions. So the basic of geomechanics refracting. So in the in the workshop theme, I just extended that definition of geomechanics. You guys already explained that geomechanics very well. So I just added a couple of things. So geomechanics is basically study on the behavior of rocks and reservoir due to applied stresses and any like change in the fluid pressure, so which basically impacts your mechanical behavior and also the mechanical behavior, basically particularly mechanical behavior, and also some geological interaction with the formation like kind of also the chemical reactions, thermal reactions. This can also come in under study of geomechanics field. So in petroleum and geothermal reservoir development and exploration, geomechanics play a very important role. And now in the recent development of like carbon capture and storage and hydrogen energy storage underground, like subsurface energy storage areas, geomechanics is very important role, and it's like big challenge to develop this the subsurface energy area. And I'm sure that there have been significant consideration and development need to be done in terms of the geomechanics in this subsurface energy storage. So let's say what's the area of reservoir geomechanics mainly where the geomechanics mainly need to be studied very carefully. So some of these areas like where we have the hydraulic fracture or natural fracture simulate like modeling, and also we need to look for the well bore stability. Let me take my here also it impacts also the well bore the stability things, and also like fault activation, where the geomechanics play very important role, and also the induced seismicity. When we inject in the fault, they start slipping, and the slipping can cause microseismic events, so which basically can lead to the micro earthquakes. And also it's important to calculate the subsidence of the subsurfaces due to reservoir depletion. And additionally, the geomechanics play important role to control sand production near wellbore, and also in terms of the wellbore stability. This kind of important area where geomechanics play very critical role. So now let's see what the importance of refracturing, which is the topic of today. So refracturing of horizontal well is a technique to enhance the production in unconventional well, and it has been proven in unconventional well for many years that refracturing is very positively impacting improving the reservoir production. So this is one study conducted by Craig et al. In Wise County, Texas, and they did like the production analysis from this 13 well, and this is the time where they started refracturing, and we can see based on after they started refracturing, their initial production was significantly improved from 0.5 mmCFD, and then after further it was also like this is was production before refracturing, and this showing the production after refracturing. So we can see when they refractured these wells, the productivity was significantly increased. So that's what we are going to talk more about refracturing today. So So the fundamental concept what we need to study in the refracturing design is basically the poroelastic effect. So instead of refracturing, poroelasticity effect is play also the very important role. So poroelasticity, we can say, is subset of geomechanics area, and which basically play very important role in when if you want to like stimulate reservoir, create a stimulated reservoir using hydraulic fracturing, natural fracture activation. And poroelastic effect is also important in wellbore stability, pore pressure, and fracture gradient prediction, and fracture-driven interaction. I will discuss more about the FDI, fracture-driven interaction, during further in the talk, which is basically the main component in the refracturing design. And also the poroelastic response is very important when we inject in the reservoir. Are we producing reservoir? Because as we increase or decrease the pore pressure from the reservoir, it's change the stresses. And as the stresses are changed, stresses and particularly the effective stresses are changed, they will can activate natural fracture and also can cause some other kind of instability. So this where the poroelastic effect play a very important role. So and also like I said in the refracting and sometimes prediction of pressure data also important to use the poroelastic effect using the pressure data to draw conclusion about in situ stresses and net pressure in hydraulic fracturing design. So I'm going to talk more about refracturing design today, which is focus of today's talk. So one of these basic concept what we need to understand in the poroelastic effect is the Biot effective stress loss, so which basically says uh, if we apply some the external load on the rock, some of the force is taken by rock matrix, and some of this goes to fluid pressure. And the behavior of the rocks basically is controlled by these effective stresses, not with the total stresses. So this play Wert effective coefficient effective law, which is represented here, is like the backbone of all this poroelastic analysis. So main part we like need to study in the poroelastic effect is the failure of the rock due to change in the pore pressure or increase or decrease in the pore pressure. So as we see, if we keep the stresses constant, and if you are increasing the pore pressure, you and we this one is showing Morse Coulomb failure criterion, how the rocks behaves. So let's say this is our current stage, and if we we increase the pore pressure, your effective stresses is going to decrease. So as a result, your failure envelope will move to this left side, and it can reach to this failure envelope, which can cause shear failure, shear failure of the rocks. So, so let's see. This is one situation where we can see the shear failure basically they can occur both in uh, injection. When we inject in the reservoir, basically we are increasing reservoir pore pressure. So the Morse Coulomb, this envelope basically it starts shifting towards left side. And when we like other case, when we are depleting, like we're producing from the reservoir, in this case, if effective stresses get increased and the Morse Coulomb envelope moves towards right. So in this case, basically we don't see that much extensive failure, but here here what happens, this stresses magnitudes get increased. So eventually this circle will become bigger and bigger, and it can also uh, touch the shear envelope. So this is was the basic concept we studied. I've shown about this all the poroelastic analysis required for refracturing. So now we are going to what's the basically refracturing and how we can control that thing. So like I already mentioned earlier, refracturing of horizontal well is basically used to enhance productivity of the reservoir. So so but the problem with what's problem with that, when in this cell formation we try to fracture like put the wells very close, and once we start putting the fracture very close to like to recover the maximum amount of the to extract more area of the reservoir, we try to put the wells close, and as we put them close, they start doing well to well communication interference. So in that case, it can happen some like production loss. So that's very important to optimize the well spacing, that we don't see any frac hit basically. So I will discuss more about frac hit further. So this case is showing evidence. This study was conducted by Voyager et al. In Barnett cell. I believe yeah, it was in Barnett cell. So they have did this very good study here. This well was already like producing. So it was producing, and is produce as it's produced, it changed the stresses. And then when they came back and they tried to drill another well and trying to like fracture this well, and we can see the fracture. And this is this MEQ data, this seismic event data from fracturing of this child well. So we can see the most of the events are towards this production well. So it means that if we fracture from this well, have more tendency to move to propagate towards this well. And if you keep injecting or fracturing, so they will eventually will like interact with this well. And once so that can cause the break heat and damage of this production from. Sometimes it can damage production of both well, both like this already producing well, and one which is like new well also. So we see here. So one of the basic concept what we need to study in that refracturing design is basically change of the horizontal stresses due to change in the pore pressure. So this here we say the very good study here. So we have one producer fracture here, and we produce from this one for like around like the 3 years as 15.5 megapascal constant production pressure. And as we produce from this one, we can see this pore pressure around this fracture is decreasing. And as pore pressure is decreasing, this pore pressure decreasing, and it will lead to change in the horizontal stresses. So these horizontal stresses let's say this is the original orientation of the SH max maximum principal horizontal stress, and this is when we produce, and after production, this we can near to production well we can see that the stresses are changing the directions. So now if we try to like put some well here and refracture, so they will this fracture from no let's sorry is here right now I'm explaining here. So if you want to like fracture this well again, so this fracture from this will have tendency to propagate orthogonal to maximum horizontal stresses because your stresses are changed here. So so let's see what happened with that fracture driven interaction or Frac-hit. So when we produce, like I explained earlier, when we produce a localized pressure sink or reduced stresses zone is created near this production well fracture, and if you want to do another other well here or parallel to here, and if you want to fracture that well, so the fracture from sorry fracture from that infill will get reduced stress zone towards this production well, and they will have more tendency to propagate towards the production well, like we have seen earlier in the microseismic field microseismic data. So now we see that so how this bracket happens. Basically now we can see much better in this one. So this is two cases I have. One was in normal faulting state regime, where we have horizontal state difference like just 3.4 megapascal, and other was like we have it was in strike slip regime where we have horizontal stress distribution like SH max minus SH min. That's around like 33 megapascal here. So in this first case, when we produce, we can see this reduced stress zone and pore pressure zone is creating, and also it's also changing the stresses here. So now if we want to fracture this well, the fracture will always follow the direction of local maximum principal stress direction. So now if you want to fracture this well, this fracture will have tendency to propagate in this direction. Basically, it will avoid this production fracture, and it is, since it has a reduced stress zone, it will still come to production towards production well. So this is I say this one I say the Frac to well interference when the child well fracture is interacting with the production well. And the second case we can see, because since we have very high horizontal stress contrast, so we don't see any stress reversal or any stress direction change, but still we get reduced stress zones. So if you want to fracture this well child well again, still you have the same tendency, the fracture will propagate towards this production well, and if it comes close to these production well fractures, so it will basically get interaction with this production well fracture. So this one I termed like Frac to Frac interference. So basically mainly the two types of these interactions occurs in refractoring design, and it depends on the stress conditions. I, so basically, what are main technique for refractoring design? So basically, there is mainly three type of techniques are used. Once you have the one production well, and and we already produce for some certain certain period of time, and then once this well is like not producing that much, then you want to drill additional child well and try to refracture this well, so that we can enhance the reservoir production. And other case happen when we have the like multiple like two, this one showing the two, but you can have the multiple horizontal well too. When you have multiple horizontal well or two horizontal well, and when so this like this will produce this area, let's say here, and this one produce. So some of these reservoir in between will be left. So then you can drill additional child or infill well to extract this area here in the reservoir. So, and the third type of technique, when we want to fracture the same horizontal well. So if we have some like already fracturing stages where we have the sufficient spaces between the stages, so some of this reservoir will be left here which cannot be extracted from this fracture or this fracture. So in the refracturing design, what we do, we plug these stages, and in between the area we again refracture and try to produce this well. So these are three techniques mainly used for refracturing. So I will basically discuss all this Frac-hit, basically this using the first design, and some of analysis will look with second design too. So let's see, go to some simulation examples. So here is the model which I have been developing for many years. And this model is called as GeoFrac 3D, which is like fully coupled 3D hydraulic fracture and reservoir simulator model, which basically based on the indirect boundary element method and the finite element methods method for the fluid flow. And the fracture propagation is used using the linear elastic fracture mechanics. And once this production fracture, they are assumed as a linear production, a linear joint, and their deformation is calculated using the joint model. So I will not go brief more discuss about the model or mathematics. Interested reader can go and read some of publication I will list in the last. And some of this will also I will discuss about more in the model in tomorrow's talk. So let's go what happened here. So this is a case where I have one well with the one stage with the one stage with the six fracture cluster and spacing around like 25 meter between, and then we try to produce for like using 15.5 10.5 megapascal constant wellbore production pressure, and we produce for 2 years, and then we were interested to see how the reservoir is response after 2 years. And this is showing some input parameter. I have this was Barnett again. No, this was Eagle Port Cell. No, so, yeah, it was Eagle Port Cell, and it have like a layer formation, like 5 layers of reservoir. And this is the pay zone where we have these production fractures. And let's see what happened to reservoir after 2 years of production. So this showing the big because due to symmetry, I just took 1/8 part of this reservoir, like one around this production fracture. I just took like 1/8 part of the reservoir to see what is happening in the reservoir. So this is showing a reservoir pore pressure change after 2 years of production. And we can see that around this production fracture, pore pressure is decreasing in like is in kind of fully 3D spacing. And as a result of this pore pressure, we can see the stresses horizontal, all the horizontal stresses, sigma xx, sigma yy, and sigma z. This is vertical stress. All these stresses are decreased. So now it's basically creating reduced stress zone for this infill well fracture. Suppose if you want to fracture this thing, then we have the fracture will have tendency to this one. And let's see here. What happened to effective stresses? So basically, like I explained earlier, when we produce from the reservoir, total stresses in previous slide get decreased, but effective stresses are increasing. So this is one shows how the effective stresses are changing in the reservoir. Let's see what happened to infill well fracture. That's more interesting. That what we want to okay, we produce and stresses are changed, and now what happened? So this case is presenting again like I discussed like in the two manners of the Frac-hit. So this was showing that in normal strike, normal faulting in the regime where the vertical stress is the maximum, and then SH max and SH min. This is the like stresses order of the stresses in the regime. And here, difference between SH max and SH min was like again 3.49, like in previous I mentioned. And since because we have the like less horizontal stress contrast, we can see that stresses and towards this production fracture, they are changing. So now what will happen to the fractures here? So like I earlier explained. So now if we fracture this infill well, this is another view of that production well and the fracture well. So production well, this child well fracture will have tendency to propagate towards production well. And let's see here how it goes. Let me just let's see what will happen. What is happening here. So this is some animation now. So initially the fracture is start very symmetric from child well, and because that point it doesn't have. So this is here. We don't have that much stresses change. And now once it start reaching to this reduced stress zone, and we can see that it start like deviating from the path, because it now start following the local maximum horizontal stress path. And also we can see as it's moving close, it is start giving more preferred growth toward this pressure. And if you keep continuing propagating this one, eventually it will go and it will hit somewhere this production well here. So let's see other case. So this case was is in strike slip direction, where we have horizontal stress contrast of 30 around like 33 megapascal. So in this case, we can see here, this is like zoomed out view of that stresses near to the production well. So we can see that reduced stress zone is created, but we don't have any stress direction change, because the difference between SH max and SH min is such a high, we cannot see their reversal or any alteration of the horizontal stress or principal stress directions. So let's see how the fracture will propagate in this case. So let's see here. So this case also is, so initially this case is also showing the similar kind of behavior of the fractures. Fracture is going almost propagating symmetric from this child well, and let's see how it goes once it goes further, then how it will behave. So I just is going. Let's say we can start. It is already started. I just start going towards this zone, reduced stress zone here, and it's already in this zone, and it start going preferred propagation towards this well. So in this case also, if we simulate it, propagate it more, it will basically give the second kind of frac hit I explained earlier, like frac to frac well communication. So this is I have shown now. Let's see what how we can minimize this effect. So one strategy, there are several strategies, but one strategy is what I found is very kind of effective also in the field. Some studies have been conducted. So what they say, if you preload or repressurize these, so after 2 years of production, if you go back and inject again on this production fracture before fracturing this well, so what will it will try once you inject the fluid with this one was relatively, this was simple like one study, so I use relatively high power reservoir pressure. But the key point here also, that you have your pressurization pressure have to below your reservoir stresses like SH max. So we basically don't want to fracture this production fracture again, but we just want to bring back the stresses to close to original stage. So when we pressurize this thing for 12 hours with this high pressure, and we can see that it stresses, pore pressure and stresses, they almost came to the original state. So they're like very like less change in the stresses at this condition. So now we see how. We are interested how it happen to what happened to infill well, like child well fracture propagation in this case when we preload the production well. So now we can see this. This is again the normal faulting regime, where we have just 3.49 megapascal horizontal stress difference. So we can see that we don't have any kind of stresses. They are perfectly oriented around along SH max direct direction, and we don't have any like reduced stress zone. So, but we have the stress reservoir stresses were varying with the formation. So we have some like preferred growth around in the vertical direction, but not towards the this production well fracture. Let's see in the animation how it behaves here. So let's see so now again the fracture is propagating a radial direction, kind of symmetric fracture initially because it's still in this zone, and once it start going up, we can see that this will go upward because we have reduced as this going upward is going to reduce stress zone due to like overburden stresses because we have the stress gradient. So with the which are changing with the formation depth. But now we can see that these Frac-hit like preferred fracture growth have been completely controlled with this just like preloading this fracture tip fracture production fracture before infill well child well fracture, and we can control this Frac-hit, and this have been tried in the field. So it seems working fine. So how we can detect this bracket? This is very kind of relatively new technique which have been introduced in the field. They use like low frequency distributed acoustic sensor to detect Frac-hit. So basically we have this production well here, and they put some monitor well, and here they put some fiber optics. And as fracture propagate from this production well, here they can measure the strain, like strain signal from that fibers, and based on that they can calculate if the fracture is coming towards the child well, or how fast it can. Even using this LFDS technique, they can also characterize fracture width and fracture length and all things. So this is one very good paper. I suggest if reader to go and check. This is from a study from Texas A&M, and this is very recent paper. And they have seen this kind of like dash signal where this is we can see this. So basically when this strain magnitude here going exceeding from 0 and give some positive, so they see this 5 fracture here showing communication with this child well. So they can, based on using this technique, they can detect a Frac-hit. So let's see some other parameter which impacts this Frac-hit. Are so basically the like all discussion we have seen, the Frac-hit basically occurs due to reduction of pore pressure, and the stresses are the result of resultant of the reduction of the pore pressure. So this one is the same example. We have the we just measure the stresses at this point with varying like production time. So we can see up to as we are increasing the production time, this pore pressure is decreasing and corresponding stresses are decreasing. So if you have the same kind of formation, so if you have in products for more time, and then like want to refracture, then we have more tendency of the refract, because here we can see that after certain time you can see this stress reversal is happening. So yeah, this is going the this plot is showing the horizontal stress contrast to because earlier sigma sigma yy the higher and sigma xx was minimum, and once it crosses then we see that negative horizontal stress contrast is happening after like this after like this. We can after like 1 year, around like 2 years of the production time here, we can see this stress reversal is occurring. So there is so it's like in refract design, this always have to production time also need to, based on reservoir properties, production time also need to optimize when you want to basically drill and do the refracturing of child well. So as you if you pass this time frame based on your properties, you are definitely going to be Frac-hit, because you already went to significant change in the horizontal stresses. So production time basically play a very important role here. So other thing was this example I did some simulation to look the fluid compressibility. So as we have like lower fluid compressibility fluid, so it gives more depletion, because it also depends on the diffusion coefficient. So if you have lower fluid compressibility compressibility fluid, it can reservoir, it gives more depletion, and hence it gives more stress change. And fluid compressibility gives lower stresses, lower depletion, and hence lower stress change. And also I looked with the rock compressibility, but rock compressibility was not as significant as compared to fluid compressibility. So fluid compressibility is more important as compared to rock compressibility in this case. So this one, this study is showing impact of your reservoir fluid viscosity. So if you have like low fluid viscosity, so low fluid viscosity basically gives more diffusion, and more diffusion means we have more stress change. So if you have a low fluid reservoir, then you can get this stress change very early in production time. And if you have like high reservoir fluid, viscosity fluid, it will take more time to develop this diffusion and stress rotation. Like we have seen here in 3 years of production, this low viscosity reservoir is giving significant stress reversal here, but in this other case, we haven't seen any reversal yet, and that plot is shown here in this plot 2, XY plot 2. And this one again is basically we already seen earlier, but this is again showing the horizontal stress contrast. So if you have high horizontal stress contrast, so there is very, so what is happening here as you produce both. So this part, this is very significant is part here in this sh sh min stress, because near to this production fracture, this production fracture tips close, so some of this part of this sh max they get increase, and that's happening due to fracture tip effect. But overall after you pass this like production fracture tips, this sh min is also decreasing, sh max both are decreasing with the production. But in low, in higher horizontal stress contrast, we have significant difference between stresses, so we don't see much like change here. But in low stress reservoir, we can see that this here maximum horizontal stress component, this is crossing, going below with the minimum horizontal stress. So now stresses are changed here. So like we have already seen earlier simulation that if you have low horizontal stress, there is more chance of stress reversal and the Frac-hit. So like basically this will give more well-to-well communication here. So this one, this study shows a case of like reservoir permeability, and reservoir permeability directly have the impact on diffusivity. So if we have low permeable reservoir rocks, we get less diffusivity. So we can see even the same with the same production and same production time and production pressure, we don't see stress change or stress reversal here, but the high reservoir permeability is showing the stress reversal in this case. So this is all the sensitivity analysis. Let's see one field simulation of this Frac-hit. So this was one case study in Kingfisher County in Oklahoma state. There they have this pilot well, like there's still 12 well was had this configuration, and this was like mainly in Meramec formation. Let's see what happened with this kind of configuration. So this is so here this one was the field configuration of the wells, how these have been oriented in the field. And let's see what happened. So I did basically two cases here. So this was the field is field pattern which we say the staggered pattern. Other one can be when we have this perfectly, like there is no offset between, let's say this well, and this well, they are all in the same line, so that called as stacked well. So this one simulation here showing the stacked well, where the like other wells are like completely in the same one line. But in the other case, so this is showing the pore pressure change after 1.5 year from this stacked well, and this one is showing the stress reversal. And in this case also have stress gradient. So as we see, we cannot see that effect like we have seen earlier very clearly that stress are changing. But in next plot I will show that near these wells how stresses are changing. So this one was like I said, this is like the random pattern where they are not, the wells are not in the perfectly in the same line. It's kind of a staggered pattern. So let's see. Yeah. So let's see here. This one I took this part of this wells here, 4 wells, and zoom out the stresses near stresses. These are four production wells. This is where I want to put a infill well fracture and see how stresses are changing. So we can see this pore pressure here. This because this if you calculate the like distance from this well to all 4 wells, so this was the nearest from here, and this direction if we see more like is production reduction zone is very much closer as compared to these other remaining wells, and the same is happening with the stresses also. We can see stresses are more like decrease towards this production well, and let's see how the fracture will behave in this case. Let's see here. So this is showing the animation from that particular small part of that stagger well pattern, and now we can see how the products like the infill well fracture is propagating in this case. So let's say we can right now the fracture is already started tendency to propagating towards this well, like we have seen in an earlier plot that this was the lowest stress zone, and now as this move further it just get like close to this well, and eventually it will do the frag hit with this particular production well. If you keep propagating, it can go with these others also, but the first it will get will hit this production well, which is close to this infill well. So this is what I did all this analysis in this research, and I'm glad to present. So here are my conclusion from this research. The refracturing of horizontal well is well-proved technique for production enhancement, and like we have seen that production from the production wells create the pressure sink, which basically creates a reduced stress zone for the child or infill well fracture, and which will lead to well to well communication. And this is very like one of the biggest challenge in the shale reservoir development going on here, particularly in the United States. The Frac-hit issue is a very big issue, and almost all the players they have to invest on the mitigation of this Frac-hit, and which for effective production from this reservoir, this Frac-hit issue is very critical, and it need to be effectively need to be mitigated. And I also we see that we already seen that preloading of parent well before infill or child well fracture can mitigate the Frac-hit issues, and we have seen that several parameters impact this stresses change, which can be also optimized based on the reservoir to reduce this Frac-hit or well-to-well communication problem. So we, based on this analysis, we can conclude that geomechanics play a very critical role in refract design and optimization, and which need to be taken care to enhance your reservoir production. So interested readers are recommended to go some of my recent publication on this topic if you need, and also if you need, we can directly contact me. Uh, so uh, so this research was partially funded by my the department and industry partner GIP consortium. That support is highly appreciated. And if anyone is interested, can reach to me at my email, and then I'm open for any question or comment. Thank you. And I really thank you to Harsh and all our organizers to giving me a chance to present this research. Thank you.
Thank you, Dharmendra sir, for conducting
Yeah.
this workshop and sharing your insights on geomechanics. If anyone has doubts, please ask. Sir, we have a question from Shlok Panchal
Okay.
saying how are fracture shapes influenced by faulting regime.
What is the fracture shapes?
Yes, sir. How are fracture shapes influenced by faulting regime?
Yeah, they are highly impacted with the fracture regime. So basically, it's basically the stress magnitude which basically impact the fracture shape. So because this was one study which where I just assumes very perfectly production fractures, but in reality they will be not that much symmetric. So they will be highly impacted with the reservoir stresses and reservoir regimes. Yes, so of course. Did I answer his question?
Yes, sir.
Okay. Yes. Thank you. It's a nice question. Yes.
So I have another question.
Yes, sir.
In
So
the
go ahead.
actual cases,
Yeah.
what kind of the fractures are created in the formation, whether it is a shear fracture or tensile fractures?
It depends on the reservoir. This is basically it depends what kind of reservoir you are simulating. So in this the oil and gas, mostly they are tensile fractures. But if you go to other geothermal thing, which I will discuss tomorrow, where we have highly naturally fractured reservoir. Also, if you have the natural fracture reservoir in oil and gas, also some of these fractures can be also activated due to during hydraulic fracturing or fluid injection. So there can be some of these shear induced fracture too. But mainly in the oil and gas hydraulic fracturing, they are tensile fracture.
Okay, sir.
Sir, we
Yes.
have a doubt from Ishan. He's
Okay.
asking how pore pressure is related to stress.
How pore pressure is related to stress? So if you do like fully coupled analysis, they are directly coupled. So if you change the pore pressure will change the stresses, and the other way change in the stresses will impact the pore pressure. So they are like fully coupled, but in the order of magnitude of the pore pressure impact more the stresses. The other part is not that much the influence of the change in the stresses, not that much in the pore pressure, but they are like they are coupled processes. So change of one is it will impact other one, and like we have already seen in that basic concept in bio effective stress law. If you change the pore pressure, we can go to the slide. So we can, I don't know, this was we just yeah. So it's good question. Let's see. Yeah, here. So if we so they're fully coupled. Change of pore pressure will directly impact the stresses, and also if you look other way, if you change the stresses, it'll impact the pore pressure.
Ayub is asking if you can
Yes.
share the PPT with us.
I have to check. If somebody is interested, probably can read the some of my papers, but I will check with if there is not any issue with my department or something, then I can definitely will share. I'm not sure at this moment, frankly speaking. Yeah, but let say him give my email and he can be in touch with me.
So I would like to extend our thanks to always supportive audience for participating and making this workshop a success. For the second day of our workshop, we hope to see you all at the same time tomorrow. Thank
Yeah,
you again.
thank you. See you all again tomorrow. I hope that you can join tomorrow. Thank you.
You all may leave now. Thank you.
Thank you.